AQA A-level physics. This is for the engineering option, and this video is about the second law of thermodynamics and heat engines. And this is the chunk of the specification we're going to be looking at. So what is the second law of thermodynamics? Well, heat will only flow spontaneously from a higher to a lower temperature. If I have a hot cup of coffee and I put it down on the table, it will lose heat energy to the surroundings, and the coffee will get cooler and the surroundings will get a little bit warmer. Okay, so heat energy naturally, spontaneously flows from hot to cold. You can get heat energy to go the other way, but to do that you would have to do work. Okay, but without doing work, and we'll talk about heat pumps later on, without doing work, heat flows from hot to cold. Now, if I put a cold cup of coffee on the table and I came back later and it was nice and hot, if a cup of coffee absorbed heat from its colder surroundings and became hotter, now that actually wouldn't go against the first law of thermodynamics because energy would still be conserved, but it would violate the second law. If you do engineering at a higher level, or if you're doing chemistry, you'll know all about entropy, won't you? This natural tendency towards disorder, a natural tendency for energy, the energy in a system to kind of spread out, to dilute. So, heat engines. What is a heat engine? Now, we've already looked at a couple of heat engines. A heat engine is any device that converts heat energy into useful work. So, a petrol engine or a diesel engine is a heat engine. You have hot gas in the cylinders, pushing the piston out, doing mechanical work. A steam engine is the same thing. You've got steam, hot steam, pushing the piston outwards, and a steam turbine. These are all heat engines doing work, producing work for us. This schematic diagram, look what's happening here. You've got a high temperature reservoir and you've got a cold temperature reservoir, or you could say you've got a source, a high temperature source of heat energy, and you have a cold temperature sink. And heat energy will naturally flow from the high temperature to the low temperature from the second law. Heat energy flows spontaneously from a high temperature reservoir to a low temperature sink. Now, in a heat engine, basically, we use that to do work. So in between, just on this diagram, we have our heat engine, which acts a bit like a turbine. And as the heat flows from hot to cold, we get it to do useful work. An analogy would be this water turbine. As the water flows from high to low, it's producing mechanical work for us. Okay, so in a heat engine, we use the flow of heat to do mechanical work. And the work that we get is QH minus QC. The heat that we get from the hot source, QH, minus the heat that goes into the cold temperature sink, QC. Now, not all of the heat can be converted into work. If you think about it, you want the heat to flow, and if we want a flow of heat, it's got to go somewhere. Okay, so not all of the heat can be converted into work in a cyclic process. Looking at this indicator diagram, which you should be pretty familiar with by now, W is the work done, and then we have Q in and Q out at the bottom. So as heat flows from hot to cold, not all of it can do work. There's always some waste heat. There is a maximum efficiency, and the maximum efficiency is less than 1. Here we're deriving the expression for the maximum efficiency. So it's useful divided by input. So QH minus QC which is, we said, the work done, divided by QH. And so we get this expression here. QC is the energy that we lose to the sink. QH is the energy that we get from the reservoir. And we can convert this to Kelvin, because in Kelvin, Q and Kelvin temperature T are proportional. So the maximum efficiency must be less than 1, and the maximum efficiency is 1 minus Tc over Th, where Tc is the temperature of the sink in Kelvin, Th is the temperature of the hot sauce, okay? I'm not talking hot sauce at Taco Bell, I'm talking where the heat energy is coming from, and that is our maximum efficiency. Don't forget, it's got to be in Kelvin. From looking at this equation, how can we maximize the efficiency of the heat engine? Well, clearly, we want this fraction Tc over Th to be as small as possible, don't we? So we want a hot source, and we want the temperature of the stuff coming out of the exhaust to be as cool as possible. And then we're basically using as much of that heat energy to produce work as possible. Here's a question for you to do. Have a go at it yourself. Show you the answer in 3, 2, 1. And there you go. So that's your maximum efficiency. Now, practically, for a petrol engine, how can we increase the efficiency of an internal combustion engine? Anything practically we can do? Well, one thing I've already talked about is we want a high compression ratio. Do you remember what that is? That's like the big volume divided by the small volume, the compression ratio. Now, why? Because if there's lots of compression of the gas, then it can get hot before we even burn the fuel. Okay, so that's going to be more efficient. Also, when it expands, it's traveling a bigger distance, so it can do more work. So this is why a diesel engine is more efficient than a petrol engine, because it has a much higher compression ratio. We want complete combustion of the fuel, okay, producing a high temperature gas. And this is basically a lot to do with the carburetor. The carburetor adjusts the mixture of air to fuel. Okay, and you can make a big difference to the efficiency if the carburetor is correctly adjusted. Also, the timing of the engine. There's valves opening and closing, letting the fuel air mixture in, letting the exhaust out, making sure the spark occurs at the right time. All of that engine timing should be adjusted optimally. Yes. And also getting rid of the waste gases. That should be done efficiently as well. We don't need them. Get rid of them quickly so that you get the good stuff in for the next cycle. Combined heat and power. Well, what's that? Well, we've said that energy is always wasted. Is there anything that we can do with this wasted heat energy? Well, maybe you could use it to, for example, heat houses. Here's a power station making electricity. Maybe that waste heat energy, you know, don't send it off to the cooling towers, send it off to the houses nearby, and it can do their central heating for them, or go to greenhouses to keep them warm, to grow vegetables or whatever. Another example is a turbo in an engine. You use the waste heat from the engine to warm up the fuel air mixture, and it makes the engine more powerful and more efficient as well, a turbo. But be aware of what combined heat and power is. It's using the waste heat to do something useful.